Okay, this is a topic of temperature and measurements. In this topic, we will see this parameter, which is one of the most important in any process control or in a smart home, which also requires temperature measurements. So an accurate temperature measurement is not easy to obtain with accuracies better than 0.5 Celsius, and great care is needed. So errors occur due to several sources, such as the sensor non-linearity, temperature gradients, calibration errors, and poor thermal contact. Okay, so we will see the scales first, because when we are working with temperature, we need to know the temperature scales. So the unit of the fundamental physical quantity known as the thermodynamic temperature, T, is a Kelvin, symbol K, defined as a fraction of the reciprocal of 273.15 of the thermodynamic temperature of the triple point of water. So we will see what is the triple point of water. Most people think in terms of degrees Celsius. The relation between Kelvin and Celsius is this. So if you have a Celsius, centigrade degrees, and you add 273.15, you convert that temperature into Kelvin. Okay, so this is the conversion equation or formula to convert from Celsius to Kelvin. So, and from equation 2.1, which is this one on the top, it is clear. It is clear that the triple point of water in degrees Celsius is 0.01 Celsius. So, from a practical point of view, the ice point is 0 Celsius, and the steam point is 100 Celsius. So that's the best way to understand the temperature scale in Celsius. So some commonly known temperature points are these. So look at here we have the scale. So we have the absolute zero, the ice point, and the water boiling point. And the ice point is water ice point. Okay. So the ice point is 0, and the water boiling point is 100 Celsius. And the absolute zero in Kelvin will be 273.15. Now, the ice point in Fahrenheit is 32. And the water boiling point in Fahrenheit is 212. Okay, which is in Celsius, this is the absolute zero. Now in Kelvin, here is Kelvin. So in Kelvin, we have the ice point is 273.15, and the water boiling point is 373.15. Okay, and the absolute zero is 0. So that's why we call this the triple point of water, because you have the absolute zero, the ice point, and the water boiling point. Okay, on January 1st, 1990, a new temperature scale was introduced known as the ITS 90, the International Temperature Scale. So this scale supersedes the International Practical Temperature Scale of 1968. Okay, so the ITS 90 resulted in changes of 1.5 Celsius at 3000 Celsius. So this is why because now we have better equipment and with more accurate equipment to take those measurements. So in this table 2, that 2.2, we have the fixed points adopted in the ITS 90. So we have the hydrogen triple point, the hydrogen boiling point, at this pressure, and neon, which is a gas, the oxygen. It is important to know oxygen. Okay, and remember we have temperature in Kelvin and Celsius. So we have other things. Right here we have water, okay, the triple point water. And these materials are used in the manufacturing of electronic components, chips, semiconductors. We have other triple points for aluminum and for silver, for gold and copper, okay, because copper is widely used in electronics. Okay, now the types of temperature sensors. Okay, this is section 2.2, types of temperature sensors. There are many types of sensors to measure the temperature, and we need to know which one to use depending on the scale we're going to be working. So for example, in this table, which is a very important table, we can determine the type of sensor here. So we have a thermocouple. The temperature range is this, from minus 270 to 2600. This is the accuracy, plus minus 1 Celsius degree. The cost is low, and the robustness is very high. Okay, so an RTD works from negative 200 to plus 600. Okay, so RTDs are very common. This is the accuracy. Low cost, the cost is medium, the robustness is high. A thermistor, which is the one we will be using in the lab, it's from minus 50 Celsius to 200 Celsius. This is its accuracy, low cost, robustness is medium. An integrated circuit, there are many types of semiconductors, like the classic LM384 or LM35, which we will use in this class for some experiments. Those work from negative 40 to 125. The accuracy is this. Today we have even better accuracies than 1 Celsius, and the cost is low. Okay, so this table is important for all of you to take a decision depending on where you will be using a temperature sensor. For smart homes, thermistors and integrated circuits are the best option. Okay, so this table is it's a summary of all the details of a thermocouple, which has a wide operating range, low cost, rush. These are the disadvantages. Okay, nonlinear, low sensitivity. So by nonlinear, it means you cannot connect it directly to a measurement device. You have to make it linear. Okay, there are some op-amps that allow you to make it linear. Okay, the RTD is linear, you see, but it has a slow response time, a wide operating range, high stability. The thermistor, which is the one we're using in the lab, it has a fast response time, which varies from 2 to 10 seconds. Low cost, small size, large change in resistance versus temperature, but it is non-linear. So we have some techniques we will see later to make it linear. Okay, it requires a current source. We will see what is a current source. Okay, and limited operating temperature range from negative 50 to 200 Celsius, and not easily interchangeable without recalibration, so we have to recalibrate it. And the integrated circuit, the LM34 and LM35, they are highly linear, low cost, digital output sensors. There are some that already have an A to D or digital output. They send a stream of bits indicating the temperature, and they have limited temperature range, voltage, current source, voltage or current. In this case, we only apply voltage. And sometimes they have self-heating errors. Okay, not good thermal coupling with the environment, yeah, because they have to be attached to sense the environment. Okay, and there are some examples here which are for you to read and do your homework in this chapter. So please write down those into your notebook. And there are other topics like measurement errors. What is a measurement error? What is how do you calibrate errors? Sensor self-heating, okay, which is those topics we will see later, and also the topics of electrical noise, mechanical stress, thermal coupling, how do you solve those issues, sensor time constant, how many seconds does the sensor requires to change, to respond to a change in temperature, in the external temperature, okay, and sensor leads, and another topic is selecting a temperature sensor. We will see those in another video lesson. Thank you.